I love how we each have our own deeply concentrating looks.
Yeah. How do I, wait, what? What? How?
You get squinty-eyed and I do weird shit with my mouth.
We're live, by the way.
Okay.
Sailor face. All right. Yeah, I know. You're just, people. Think people suspect that you're the one with the potty mouth and not me.
You had children.
Yeah, that's exactly right. I had it trained out of me. That's right. You're just like, you spend 15 years carefully watching what you say. Yeah, it's funny. And then at a certain point, you hit a certain age, and then you just relax it again, and you just like, Dad, like what? Welcome to adulthood. You can vote, you can drink, you can hear Dad swear. Um, we had the weirdest weather today. It was
What
like,
happened?
well, it's just like in one day we've had rain, we've had
Mhm.
freezing rain, we've had hail, snow, and then sunshine. And like I was out in it, and it's the weirdest thing. It's like being someone's like throwing sand at you, but wet sand. Someone's throwing wet sand at you is what.
Sleet. You had sleet.
Yeah, we call it freezing rain here
Yeah.
in Canada, and it's like right on the edge of rain and rain and snow or rain and hail. I forget. Like, wait, one is hail that's melting, and one is snow that's melting.
So hail forms high in the atmosphere
Hmm.
when there's atmospheric cold and you can get it in the summer. Sleet is rain at higher altitudes that freezes on the way down.
Right. I don't know. It was weird. We have weird stuff in the springtime here in Canada. It's the best time is like in Marchish, March, April, and then because like in the wintertime it's just this gray haze everywhere in the sky. Like it's just overcast. It's either raining, threatening to rain, or it just rained. And in the summertime it's clear, perfectly blue skies, and we won't get rain for 4 months. But in the spring and the fall, it's just like huge fluffy clouds. It's really cool. And it freaked Carl out when she first came here because back in Texas, big fluffy clouds mean thunderstorms, but
Death,
not here.
yes.
Yeah, but not here. So big
Yeah.
fluffy clouds just mean big fluffy clouds. You can have a huge towering mountain of clouds and it doesn't mean anything. So yeah, it's
Yeah,
very
we get thunderstorms and tornadoes here too.
yeah, tornadoes. No, I'll take earthquakes over tornadoes. I know you wouldn't, but
Yeah, you can get out of the path of a tornado.
yeah, but earthquakes aren't that bad until they're bad. Yeah,
Exactly.
yeah.
Exactly. That Cascadia fault line near you terrifies me.
Be in like a 25-story tower in the middle of an earthquake when the whole tower is just creaking back and forth, and you're just it was built to handle this. It was built to handle this.
Yeah, yeah. I was in a Soviet apartment building during a fairly significant earthquake, just 3 floors up, and that kind of gave me a new respect for earthquakes and less respect for Soviet construction.
Right. Right. Yeah, I know. It's just the opposite. You could hear the bones of the building creaking back and forth, the steel girders, and you're like, okay. And there was no cracks. Some books fell over, but apart from that, it was fine. Yeah, tornadoes though? No, thank you. Nope. Canes are the worst. Like if I had to, hurricanes would be bad too because they're just like they're gonna. I mean, you can run from them, but they're also like, are you gonna come back to a house? You don't know.
And they have tornadoes within them.
Right. Yeah. 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 I
Yeah.
guess if they like somehow had also earthquakes, that would be trouble. Anyway,
Since we're not like doing the show yet, I have to show everyone just the cutest thing ever. Hold on. She's totally asleep between my camera bag and shop vac,
yeah.
and she just exactly fits right there.
Someone's saying they're getting buffering. I don't see any dropped frames on my side. So somewhere in between in the YouTubery. Yeah, so I guess we should explain what we're doing. We're recording a day early, or actually like 3 days early,
4.
4 days
Yeah.
early, because we're going to try to change the schedule. The problem that we have is that the way that goes from when we record to when we release is too short. So we're going to try to change the release schedule. So we're going to push back the release schedule probably a couple of days. So we'll release on
We're going to figure it out. We're going to make no promises
yeah,
today.
yeah,
We're
yeah,
just trying to get ahead
yeah.
because we like Rich, who does our audio, and we like Allie, who does our video.
Mm-hmm.
And Allie likes her weekends, and I don't blame her. She's kind of like a newlywed and stuff like that.
I,
So we're going to let her have her
I don't even know what that
weekends.
means. Like, like your weekends. Anyway, weekends are this. There's no difference between in
See,
my life.
she lives at a private school that her spouse is IT for.
Yeah,
And so they essentially live at Hogwarts, so weekends have an actual meaning.
right. Yeah, yeah. No. There's literally no difference between weekends and weekdays for me.
Yeah.
Um.
Fewer press releases on weekends.
Yeah, I guess so. I mean, I do work a lot less on the weekends, but I still work. um. I should mention. So I'm going to be interviewing David W. Brown on Thursday to talk about The Mission, which is the trials and tribulations that went into getting the Europa Clipper approved. And
Oh,
it is
that's
so
cool.
good. Like, it's on my favorite books of the year list already.
I can't believe they have a book before they have a spacecraft.
Yeah, but this is not. So it's called The Mission, or How a Disciple of Carl Sagan, an ex-motocross racer, a Texas Tea Party congressman, the world's worst typewriter saleswoman, California mountain people, and an anonymous NASA functionary went to war with Mars, survived an insurgency at Saturn, traded blows with Washington, and stole a ride on an Alabama moon rocket to send a space robot to Jupiter in search of the second Garden of Eden at the bottom of an alien ocean inside of an ice world called Europa. A true story. It's
I'm just going
awesome.
to move along from that.
Yeah.
Okay.
No, it's a super good book. It's so funny. Yeah, he's a great writer. Okay. So anyway, if you're wondering what it is you stumbled into, this is going to be a live episode of Astronomy Cast. We're going to record the show, including some commercials. I don't know if Nancy's there to tell me. Okay. And then we will stick around and answer your questions about space and or astronomy. And this time I promise we will answer questions about space and or astronomy. Do you have anything special that you wanted to mention before, as we do the show?
No.
No? Okay.
I'm in the middle of attending a conference in addition to everything else, and my brain is just currently.
Yeah. Attending a conference without leaving your house. Welcome to COVID era.
Yeah.
All right, I'm going to press record.
I'm looking for my record button.
Wait, am I going to stop for commercial after the intro? I forget what we did last week.
Uh, before you go into the intro.
Okay.
When we come back.
Okay. Sounds good.
Okay.
I pressed record. Hello, Richard.
I have pressed all the record buttons.
Whoa.
All of them.
All right, here we go. Astronomy Cast, episode 593, Stellar Parasites. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. I'm Fraser, Cain, publisher of Universe Today, and with me, as always, is Dr. Pamela Gay, a senior scientist for the Planetary Science Institute and the director of CosmoQuest. Hey, Pamela, how you doing?
I'm doing well. I think I'm one of the few people in the US who didn't get snow today, and I'm kind of okay with that.
Yeah, we were talking before the show that I just got all the weather. I collected the whole set. I got all the Pokemons of the weather. Sleet, freezing rain, hail, snow, sunshine, rain, everything. Yeah. So don't worry, I got you covered.
It works.
All right.
I just have gray. I have lack of anything.
Yeah, that's standard West Coast Canada weather. All right. Well, we're going to get on with the show in a second, but first, let's have a commercial break. And we're back. All right, so stars often come in groups of two or more, and if they're orbiting close enough to each other, one star can feast on the other. And when that happens, well, mayhem ensues. Now, I actually had a little bit of a difficult time writing this introduction because in the olden days, you would say the vast majority of stars are in binary or multiple groups, but that's no longer true. The vast majority of stars are singletons because the vast majority of stars are red dwarfs, and red dwarfs are largely singletons. The main sequence, sort of the, stars like our sun or especially the heavy stars, they come in multiple partners. So I was trying to think of a way to say this, but I just couldn't.
Yeah, it's trickstery because the kind of thing that we're talking about today only happens when you have stars that are big enough to evolve. And a red dwarf star that formed at the beginning of the universe would still be out there happily doing its red dwarf star thing. For better or worse, the first generation of stars only came in extra large. So we don't have any of that first generation red dwarf, but there's lots of really aged red dwarfs out there, and they're really polite, and they tend to be all alone and not eat one another.
Right. And so if someone tells you that, hey, did you know that most stars are actually in multiple star systems? You could say, no, that's not true anymore. Sorry. But
most large stars,
stars like the sun and bigger, are in multiple groups. And so and most of the time they're fine. They're far apart and everything is fine. But every now and then they get close to each other and then we got some problems. So set the scene. When do we get problems?
We get problems when one star finishes doing all your standard nuclear reactions in its core, runs out of life, and becomes a small, hungry beast. Now, to put all of this in more scientific terms, stars of different sizes go through their fuel at different rates. The bigger the star, the faster it burns through the fuel in its core. And a star can only fuse so many things in its core before it hits the point that it has an iron core. And when you try and fuse two atoms of iron, the iron is like, nah, I'm not releasing any energy. You can't do that to me. And when fusion no longer generates power, when it no longer generates energy to support the outside of the star collapses, you get a supernova if it's really big. Or if it's a smaller star that simply hits the point of, I've fused my core up to carbon and I don't have enough gravity to go any higher up the periodic table. In that case, it just kind of exhales its outer envelope and you're left with only the core of the star behind.
I just want to stop on that for 1 second. I know this isn't what this show is about, but that idea of a star like our sun bloating up as a red giant and then just puffing away those outer layers. Like when you think about the sun, it's got that core where all the fusion is happening. You've got that radiative layer where light is bouncing around inside, and you got that outer convective layer. And that radiative layer and the convective layer they just puff away. And what you're left is the fusion engine at the heart of the sun, just laid bare to the universe. It's such a crazy idea. And that's a white dwarf.
And one of the awesome things about this is because our solar system is one with planets, it's essentially going to form an hourglass-like structure. So these systems that I'm talking about that have this white dwarf core next to another star all have or had at some point in their history, because planetary nebula aren't forever, had this planetary nebula that was some extraordinarily complex shape associated with it. So you have two stars. One is a little bit higher mass, so it's evolving faster, or a lot higher mass. It doesn't matter. It's bigger. Bigger star evolves faster. By hook or by crook, it gets rid of its outer layers, and you're left with this extraordinarily dense leftover.
Right. So in all of those cases, you're left with, in the white dwarf, core of a star. In case of a neutron star, you're just left with a degenerate, tiny little ball that's spinning around.
Manhattan-sized blob.
Right, exactly. And once again, if it's all by itself, then that's just what it is until it dies, turns into whatever else it's going to turn into. But so what kind of situation will it be in to have a companion that you're going to run into some kind of situation?
Well, for some reason, probably having to do with all of that material that it's given off in the past, it has a chance that it could spiral closer to its companion, or much more likely, its companion, as it gets older, is going to expand out in size until one day, as it's expanding in size, becoming a red giant star, its outer atmosphere gets within gravitational reach of that jealous companion.
Right. And we know that, for example, with the supergiant stars like Betelgeuse and things like that, I mean, they extend out beyond the orbit of Jupiter, all the way out to Saturn. Some go beyond Saturn. And so you can imagine if there is a binary companion and the stars are close together, you could easily have one star orbiting within another star.
And you don't even have to have one star within a star to talk about the things we're going to talk about today. All you need is the dense object, the other object, and gravity.
Mm-hmm.
And what happens is that companion star, as its atmosphere begins to expand out, it hits this point first where the atmosphere is exactly balanced between the little companion and that bigger star, the lower mass star, and the core of that lower mass star. This is called filling the Roche lobe because it's lobe shaped,
right.
And the person who figured it out was named Roche. Now, if they get even a snert with the surface of the bigger star closer to the compact star, matter will start flowing from the one star to the other and spiraling in. There's no direct fall. It's a spiral in. And depending on how the stars are working, lots of different horrible things that are glorious scientifically can now take place.
All right. Well, we will talk about that in a second. But first, let's go to a break. And we're back. All right. You promised all kinds of glorious things, which, I mean, in your disaster-addled brain makes me a little nervous. So what you think are glorious, some others might see as the apocalypse. So what happens?
So one of my favorite examples of this is there was recently, since 2015, I discovered a situation where there was a brown dwarf star and a white dwarf star side by side. And it was realized that brown dwarf, this is a star order of 80 times the mass of Jupiter, no longer capable of having sustained fusion in its core. It didn't start out that way. Instead, it started out as a quite happy, regular, everyday star capable of undergoing regular, everyday nuclear fusion as stars do. But as that white dwarf got a little too close, it just started stripping and stripping and stripping its companion until its companion's like, whoa, I don't have enough mass left. I'm a brown dwarf.
So a stellar companion turned a main sequence star, it downgraded it.
Downgraded
to a
it.
brown dwarf. That's crazy. That's amazing.
And the universe likes to surprise us with all the crazy combinations of things that are possible. So we have cases where that white dwarf can completely strip down its companion. We also have cases where that white dwarf will, as you've alluded to earlier, pass into its companion. One of my favorite cases is one that we discussed earlier this year, where while I said that the two stars evolving next to each other, the higher mass one evolves down into a compact object first, and the lower mass one evolves slower. That assumes these two objects formed together. In
Okay.
high density regions, you can have two stars that formed completely separately, gravitationally come together and become a binary star late in their lives, which means you can end up ever so rarely in situations where you have a white dwarf star that evolved who knows where. And then you have a massive young companion star.
Okay. Okay. Right, because the massive companion stars, you're going to expect them to blow up. So it's very rare to see one with a partner.
Now,
That should be billions of years old. That seems
now,
weird.
now, the cool thing is that if you have that little tiny white dwarf star and that big old massive companion star, that white dwarf can strip so much material off while going into that other star.
Hmm.
So it's spiraling into its companion, it's consuming its companion, and they can both end up exploding.
Right. And I think we did an episode about this, didn't we?
We did. They
Yeah.
are awesome. These are called double degenerate stars.
Double degenerate. Yeah.
It goes
Twice the
boom in two
madness.
ways at once.
Yeah. And so, I mean, that's got to be really rare that you've got a supergiant star happening to pick up a white dwarf at exactly the time, because they only live for a few million years. So you've got to have some
Yes.
pretty weird circumstances. And that's why they're incredibly rare. I think we've only seen one, maybe two of these events in all of
One that we
astronomy.
knew, and yeah. So this now paints our two extremes.
Okay.
We have the brown dwarf getting formed because the white dwarf ate everything that made it into a star. We have the double kablooey of the white dwarf moves inside of its massive young companion.
Yeah.
Now, the bulk of the systems are somewhere in between.
Hmm.
In the majority of cases, you have a star that is bigger than our sun by not a lot, a star that's the size of our sun or a little bit smaller. 2 to 5 solar masses, basically, between these two systems. And the one becomes a white dwarf. The other, when it evolves into a red giant, fills its Roche lobe and just starts tearing material off. And it can do this in a cyclic way. A lot of these stars, when they evolve, they'll become what's called pulsating variable stars. And so when that star gets bigger, it will sporadically dump material
Right.
onto its companion.
So it's like filling up the feeding trough for its parasite, and then it shrinks back down, and then the companion star digests, and then the variable bloats up again, sloughs off new material into the Roche lobe, shrinks back down over and over again.
And so this is exciting. You have mass transfer, it's periodic. This leads to all sorts of cool lighting things up as the mass transfer
Yeah.
happens. But it's not as dramatic as periodic things can come. One of the other cool things that can happen when you have these two systems is this one that has filled up its Roche limit will spiral material onto a disk next to its companion. And one of two things will occur. Either that disk will transfer matter onto the star until enough transfers onto the star that it blows up temporarily,
Right. Yeah.
as one does.
Yeah. And again, we've talked about that. That's your straight up classical nova.
And the other case is where the disk periodically goes kaboom,
Right.
because the disk can actually get dense enough along that center compression area of the disk that it can support nuclear reactions. And so if the disk gets too hot and dense, it can go boom
Right.
and essentially clear itself out.
So what causes which? Like, if it's a trickle of material, it gets wound up onto the white dwarf like string going around the white dwarf, piling up on the surface until there's enough material there that it detonates as a nova. But if there's just like way too much material, it flattens out into this great big accretion disk. And if it's too much material, then that accretion disk starts to just explode with activity as well, because there's just too much material and it's starting to turn into like little mini stars all right, that's pretty crazy. Now, there is a more cataclysmic ending to this process, which we will talk about in a second. But first, we should stop for another break. And we're back. All right, so we've got the situation where we've got this one star feasting on this other star, gathering material. It's detonating, but it's getting heavier over time. This can't be good. Where does this go?
So the other case is what's called a type 1a supernova that is normal.
I love that there are abnormal ones too.
There's plenty of abnormal ones. The case of a star falling into another star that we discussed earlier was technically a type 1a supernova, but not a normal one.
From the inside, yeah.
Exactly. So with a type 1a supernova, it turns out, thanks to quantum mechanics, that electrons and protons can only get so close to one another before all of the forces that cause them to be separate particles give up and the two combine, become a neutron, and give off energy and particles in the process. And if you pile too much material onto a white dwarf star, the pressure of all that electron degenerate gas pushing out and those protons all existing, it's no longer able to support the star against the inward push of gravity. And when protons and electrons can no longer stay separate, when that electron degenerate gas can no longer support the mass of the star, it collapses. Becomes a neutron star. Things go boom along the way.
Instantaneously.
And, yes. It's
utterly,
kind of awesome.
Utterly. like we talk about when other kinds of stars explode, you're like, what kinds of remnant is left behind? In some cases, it's a neutron star. In other cases, it's a black hole. But in the case of type 1a supernova, it's just gone. Yeah. It's just 100% energy. The whole thing. I mean, I just sort of, again, think about that process, that it is like tearing itself apart at an atomic level and just detonating. The whole thing just becomes one huge bomb.
And this happens at a very precise point that is based on how much mass is in the system. And there's some variability that is related to how fast the star is rotating and things on that order. But the dominant factor is how big is that star. And just like if you have two sticks of dynamite that contain the exact same amount of explosive, the explosion they make might vary a little bit depending on temperature and humidity, but they're basically going to be the same size explosion.
Right.
And because type 1a supernovae have this consistently sized explosion, we use them as standard candles to measure distances throughout the universe.
Or so we thought. Because, and again, we've talked about this fairly recently.
We don't necessarily accurately measure distances throughout the universe.
Roughly.
We are still measuring distances.
Yeah. That up until probably the last year or so, astronomers were very confident that type 1a supernova were very standard candles blowing up when the star hits 1.4 times the mass of the sun. But now, like, maybe it's a little different. Maybe depending on the kinds of material they were made from, ones blew up a little earlier or later, depending on when they formed in the universe, which could possibly be contributing to the measurements of dark energy. It got weird, is all I'm saying.
There's a lot going on, and different episode. Complex story.
Yeah.
All the details short. There's multiple ways to measure the age of our universe. One of them includes supernova and a bunch of other stuff. The other includes the cosmic microwave background. And these two sets of observations do not match.
Right.
Thus, we have confusion.
Yeah. The crisis in cosmology, which is a whole other episode that we've done. Okay. So, but these are all sort of extremes. But can we just get a situation where you just got two stars, regular old
hanging
stars,
out, swapping matter?
Yeah.
Yeah.
Okay. Tell me about that.
So there's
Now
cases.
kiss.
There are cases out there where stars, as they evolve, take turns swapping material back and forth, where essentially you can have what was a dead star reignite if you feed material on it to it just right. And when we look at globular clusters, we see groups of thousands to millions of stars that all formed out of the same original cloud of material in the same period of time. So they should be the same age, except in these globular clusters, which are old,
Mm-hmm.
we see these weird young blue stars that for ages we couldn't figure out. And around 2000, we started to build up this picture where it appears that blue stragglers are stars that simply stole enough material or combined with their neighbor, and in the process ended up with a new young star that still has a full life
Right.
ahead of it out of the cinders of dead stars.
And so I think it's important to say, like, we know that these globular clusters formed billions of years ago, pretty much at the age of the
Yes.
universe. And so there should only be old stars. And when you think about the
Yes.
sun, our sun's only been around for 4.5 billion years. So it wouldn't have formed in a globular cluster. But they are, and yet they see blue stars. And blue stars only last for a couple of million years. So that's super weird. You shouldn't see that. And yet there's so much mayhem going on in a cluster like that that you're going to get these collisions happening. But still, is there a situation where you just got like two stars forming and one star like our sun is feeding off the material from another star? Like what if one star goes red giant and it has just a regular stellar companion beside it? Can you have a situation where those stars will feed off each other?
So that's going to be a lot more rare because they're not going to tend to form close enough to allow that kind of a situation to happen with the degenerate stars, the old stars. All the things that you go through in the aging process, if you're a star, can help you move around. If you start out with a star like our sun and a significantly bigger companion that isn't yet that cinder, but has simply bloated out to the red giant stage, it's possible that that red giant can transfer matter to its companion. And we see this in the atmospheres of stars occasionally, where they've essentially been blasted with evolved material from their companion star. But that whole filling the Roche lobe and sucking material onto the main sequence star will be more rare. But rare doesn't mean it doesn't happen.
Yeah. It's a big
Essentially, our
universe.
universe,
Every experiment you could imagine has been tried by the universe.
and our universe keeps proving itself far more creative than theorists are. Admittedly, theorists are humans, and our computers can't run that many experiments yet. But the universe keeps proving itself far more creative. And so we do see things that when we think hard about them, we're like, huh, yeah, this probably ate its companion. This was a vampire. This was a cannibal. These are words that we
Right.
use in
Yeah.
describing how stars keep finding new and innovative ways. And so far, we've largely blamed white dwarf stars for doing the
Feasting.
vampirism. But with the situation we were talking about earlier, where you can either have the disk exploding or material built up on the surface of the star exploding. Well, neutron stars, these are stars that are more massive than white dwarfs, which are about the size of the moon and the mass of the sun. Neutron stars are more like 2.5 times or more of the mass of the sun, and they're 20 miles across. That's like 30 kilometers or so. Inaccurate unit translations. Do not at me. And these little tiny dense objects are perfectly capable of pulling material off of a companion, of building up that disk that goes boom, and completely stripping down a neighbor. And because the next size up from neutron star in terms of mass density is black hole, you can put a lot of stuff on them before they explode as a supernova because they are trying to compress down into a black hole.
Mm-hmm.
And this is where you end up with even more disks that are likely to go boom.
Right, right. And again, sort of imagine like when you see a huge star, say a star with a couple of times the mass of the sun, and it's orbiting with a neutron star. The neutron star is going to be bright, but it's going to be this tiny little spot, and it's going to be the dominant gravitational force in the system between a star like our sun. And so it's like I don't know, sort of imagine like I don't know, like one of those hammer throwers, right? That's just sort of yanking the star around and around in these circles. And then it's siphoning material off and into an accretion disk around the neutron star until the neutron star has had its fill and detonates as a supernova.
And what's amazing is when we look at these things, we will see that disk of material periodically going around and blocking the light from the larger
Right.
star. And so we can see and measure accretion disks by how they interfere with our ability to see that much larger companion.
There's one other kind that I want to talk about before we wrap up. You can have a situation where two stars are so close together that it's almost like there's a connection between them, like a bridge between the two stars. They've filled each other's Roche lobes. Let's talk about that.
And these are common envelope stars. And technically, anytime two stars share an atmosphere, it's called a common envelope. So that case of a white dwarf plunging into its neighbor, technically a common envelope.
Right.
Technically.
Yeah.
But the more interesting case is where you have regular everyday stars. So two very similar massed red giant stars that expand in size. And they might have started out with a separation from core to core of twice the distance to Jupiter. But then as they expand out and their physical size starts to be so that each of them are roughly the same distance as from the center of the sun to Mars, that puts their outer envelopes close enough to really start pulling on each other. And they can dynamically affect one another's orbit this way, tidally lock, migrate closer and closer, and eventually end up with a shared envelope as their cores continue to spiral together.
Wow.
Now, we can't see inside stars. We don't always know when this is happening. We have interesting suspicions. There are a few papers out there. This is not a leading idea. It is a cool idea. There are a few papers out there saying that some of these really dusty stars that we see, like our Corona Borealis, that periodically shed massive amounts of dust and appear to disappear behind their own dust. There's some theories that these might be some sort of a common envelope effect. We really don't know. The universe will do anything given the opportunity and gravity.
Yeah, totally. Absolutely fascinating. Thank you so much, Pamela. Do you have some names for us this week?
I do. So, trying to find the right window. Hold on. I always make you have to edit this part. I'm so sorry, Rich. There it is. So as always, we are supported thanks to the generous contributions of people like you. We know that 2020 and now 2021 are not the easiest of years. And the fact that you're out there supporting our show means that we can pay Rich and Allie to put together the best show possible. And that really means a lot to us. You also allowed us to pay Hexacosacoron, Noel Ruppenthal, to do a new TV opener for us. So those of you watching this on YouTube have seen that new opener. You're allowing us to help people. Oh, it's awesome.
Okay, I'll check it out. I didn't even know it existed.
Sorry.
Yeah.
I was just trying to get the show out the door. This is why we're changing our production schedule, so that there's fewer things on fire while we try and get things out the door. Anyways, you're allowing us to make sure that there are people out there who are taken care of and allow us to keep producing science. So this week, I want to thank uh, Frodo Tenenbaum, Justin Proctor, David Gates, Claudia Mastroianni, Alex Rain, Abraham Cotrail, Joe Wilkinson, Jean-Francois Roget, Iran Segrov, Paul Hayden, Matthew Hortzman, John, Jeremy Kerwin, Brent Kenop, Omar Del Riviero, Arthur Latz Hall, Michelle Cullen, Dustin Ralph, William Lauer, Tim Garish, Marco Arasi, Mark Stephen Raznak, J. Alex Alexanderson, Brian Kilby, Grigory Singleton, Planar, Corrine Demtruk, Jason Thomas, Ruben McCarthy, Jeff McDonald, Iggy Hammock, and Wayne Johnson. Thank you all so much for allowing us to do everything we do. Thank you.
Thank you, everybody, and we'll see all of you next week.
Bye-bye. And now we save.
They saved. $5.93.
And I'm going to even stick it in the correct folder this time. Last week I sent my audio to Allie instead of to Rich.
All right.
Okay. One more time because oh my goodness. Oh my goodness.
Cute dog.
Yes. Is that not adorable?
That is so cute.
And yes, I'm wearing TwitchCon flannel pants today.
All right. So we didn't see SN9 today. We'll probably see it tomorrow.
So have they sent out the evacuation notices? That's always the first sign.
Yeah, no, I haven't heard.
Okay. Boca Chico Mary is really good about tweeting if they got the evacuation notice. And last night she had this forlorn no evacuation notice tweet.
Oh, poor Mary. They didn't force her to evacuate. Okay. All right, I'm uploading.
It really always gets me that there is a small community where Elon Musk has tried to purchase all of their houses, not admittedly at enough money they could actually move somewhere, which is a problem.
Mm-hmm.
But they have to evacuate every time he launches. So if something goes wrong, they're not in their house when it gets destroyed by a rocket.
I think Boca Chico Mary is an absolute treasure.
She is. Yes.
Did you change the position of your camera?
Yes. I showed you my dog.
No, I know, but now you're farther down.
Oh.
So I have to change where
fix
you are.
that? No,
yeah.
I can.
Yeah, that'd be
On
better.
an arm, I can fix it.
That'd be great. Thank you. Yeah. Like she was. I should interview her. Because
yes.
from what I can tell, she is a woman who lived in Boca Chica, and Elon Musk and team moved in, and she has become the most important resource that for the space community to be able to keep tabs on what's going on in Boca Chica. Live camera feeds, great reporting. She's an absolute treasure. Like I said,
yeah.
we couldn't do our job without her. And she's
yes.
been so generous to all of us to be able to use her pictures, to be able to talk to her, and just keep us all filled in on what's going on.
Yeah.
It's kind of amazing that she stepped up and served this role that needed it done.
I don't know her history. I don't know.
I don't know it either. Actually, you know what?
Yeah.
I don't know what the story is. So I'm kind of interested now. I want to interview her and find out what the story is.
And my teacup comes from Sterling Amy, who is another fabulous human who we need more of in our lives.
All right. So I think I've got the right questions this week. Jason Collins asks, could an intelligent alien civilization that evolved underground develop a space program?
Do they ever access the surface? I mean, if they know there are stars, sure. But if if they lived perpetually underground, I can't even imagine why they would try.
There's a I mean, I don't know whether, like, if you live underground and you eventually reach the surface, then
Hmm.
you will start to understand that there is more out there.
Yes.
But there are some interesting scenarios where you might not know. Like, one example is for say if you live on a place like Europa, you live underwater, the roof of your world is ice.
Yeah.
And you may realize that you can chip away at that ice and start to dig up. And but at the same time, the changing pressure as you go higher and higher will be bad for your body until you
Yeah.
reach the surface. And so
Or
you can imagine them having absolutely no concept, but their Apollo program would be melting or digging upward through the ice to figure out what's above them.
so the other thing that I think about is like naked mole rats are blind. A lot of cave creatures, cave fish have evolved to be, in some cases, not just sightless, but eyeless, which is deeply disturbing to look at when you're not expecting it. To me, other people will have different uh, reactions. So you can imagine that if a species evolved entirely underground, we know that there's all sorts of random large openings underground. And if they're completely blind, breaking through to the surface might simply be the giant cavern they can't find the edge of.
Hmm.
And you might end up with an entirely different mythology.
But I mean, we are blind to radio waves. We are blind
Hmm.
to X-rays, but we
Yes.
discovered them. So you can imagine if they're intelligent, they will figure out how to utilize other senses that they don't have. They'll translate visible light into some form they can understand. But 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 you can imagine it being a difficulty of their imagination in the first place to even think, or like say you live on a world where it's just cloudy all the time,
Yeah.
and to just and to never and you just it never occurs to you that there's anything above the clouds until you launch a balloon that's high enough that floats through the clouds, and suddenly you see a universe.
Well, and I can imagine that if you rely on a different set of of senses, you will scientifically evolve things in different orders where we had television and cameras before we had radar. You can imagine that a sightless people will develop radar first. And if you shine a radar at space, other than the occasional rock, you aren't going to see much.
Hmm.
And so it will completely change how you scientifically evolve, and it will be a different journey to get to space.
Yeah, yeah. Yeah, and you can see, like, from our perspective, we live on a planet. We have a nighttime. We have a daytime. Another example would be a
Yeah,
planet where there's enough stars in the sky that there's no such thing as night.
right.
And so you would eventually figure out to fly to space, and then you would realize that that they are stars and that there's other stars out there. Like, but maybe you'd be more ready to recognize that there are stars because you would be seeing many stars. You would, and some are close and some are far, and then some are super far away. So it's interesting. Some concepts in astronomy, you would come more readily to you than others.
Yeah.
There's a book that I've got. It's on my bookcase. I forget which one it is, but it talks about, like, what it would be like to evolve on different kinds of worlds, and they talk about some of these ideas. Arjun has a couple of questions here. One, are star cores always that dense, or is it just at the end stage that's really dense? So that was back to that idea of the core of the star being that dense, essentially turning into a white dwarf. And
So
I forget the
they
exact
don't
number.
start that dense. It's you end up with the densities of white dwarfs and neutron stars, because the star is no longer undergoing fusion and producing sufficient light pressure. Light actually exerts a pressure, and without that light pressure pushing outwards,
Yeah.
the star is able to collapse down into this supported by electrons or neutrons degenerate gas.
And I forget the numbers. I'm trying to look it up, but the core of the star accounts for like about a third of the mass of the star, but it accounts for only something like 10 or 15% of the radius of the star.
Yeah.
So stars at their core are way denser than the rest of the star. It's sort of, it really is like, it is in layers. That core of the star is where that fusion happens, and it has reached that critical density. And then outside that, you got the radiative zone. Won't allow convection, but it's not hot enough to allow the actual fusion to happen. And then outside that is the convective zone. And so all those other parts blow away, and you're left with whatever the star was able to fuse in its core. It could be helium, could be carbon, could be oxygen, could be silicon, whatever you've got in the core.
It doesn't tend to stop at those other things as often.
It depends on the mass. Like if it's
like you
a
get
little...
carbon white dwarfs, you get helium white dwarfs.
Yeah.
I don't remember ever reading about like a silicon white dwarf.
I mean, in theory, you'd get everything up to iron. Like you wouldn't get iron, but you'd probably get shells, right? You'd get that the middle shell.
I don't
and then
know
around that.
Is if you have sufficient material that you can start burning things heavier than carbon, does that open up a process that always completes an iron?
Mm-hmm.
And this is I'm now going to go down a rabbit hole.
Yeah. So that's happened to me so many times. I don't know if I mentioned this. I've actually taken to reviewing my live streams afterwards to catch everything that I didn't know the answer to, and then I just sort of, because each one of those, like I'll make a note of it. Like I'll take the question because I don't know the answer and it's such a fascinating question. Mm-hmm. And then it turns into a rabbit hole. And Arjun also asked, it's so crazy that this can happen. I wonder what the average distance is in a globular cluster. If I recall, in a globular cluster, they're a light year apart, and on average in the Milky Way, they're 4 light years apart. So much closer. If I recall correctly.
Yeah.
Yeah.
And of course it's like, where's the city center? What volume of the universe did they use to figure out the average separation?
Yeah, you just take the volume of the cluster divided by the number of stars in the cluster to give you the average distance of stars.
Right. So the cluster I get, but like the Milky Way isn't a sphere.
Right.
So
you take
what
the
did
average,
they include?
You take the average size of the disk, I guess.
But do you include the thick disk?
Yeah.
Do you include the spheroid?
Yes.
I don't know what they included in that.
Yeah. All right. Corey Albrecht asks, do regular lone stars ever capture neutron stars as companions?
It would be the reverse.
It would be the other way around, yeah.
Yes, the reverse can happen. The neutron star is the one that reaches out and goes, "Hi, may I have you now?"
Yes.
I mean, gravity, technically, the force is equal in both directions. But if you look at whose motion deviates more, the smaller object is the one that's getting the movement.
Mm-hmm. You've got essentially a point-sized object with 3 times the mass of the sun gathering a star with the mass of the sun.
Yeah.
But you need to have a pretty interesting sequence of events for it to get captured. You need some kind of 3-body interaction, right?
A 3-body interaction makes it easier, but you can, if you have just the right set of velocities and distances, have just 2 stars that grab hold of one another.
Right. Oh, Zephan
all things are possible given a big enough universe.
Is saying if the star is heavy enough to fuse silicon, then it ends up as a neutron star. Right. So maybe that's the way it goes, right? Is that if a star is so massive Like there's some minimum cutoff point where a star is so massive that when it dies, it explodes as a supernova and turns. But
So
it doesn't have to be.
what
It has to be iron, right? You have to be iron and above. You can't
so
get a
what
supernova with less than iron, can you?
you should be able to get a neutron star without having to, but
You,
then it would be puffing. I need to go read.
right,
I
but
need to go read.
I think you're only going to get a neutron star with a star that can't core collapse, and so it didn't make iron, because you don't get a core collapse supernova until you've got iron in the core. So everything up to
Yeah.
iron is stable, and eventually the star just doesn't have the oomph in its core to be able to go to the next level, and so it just stops at that point and cools down. So you will get some flavor of white dwarf until you get core collapse.
But we only have carbon and helium white dwarfs. So this tells me that there is something else going on that you and I are forgetting about or didn't read at this moment in
Right?
time.
Do they blow off that material as well as part of the outer envelope?
So
Yeah. Okay.
yeah.
Um,
They may undergo so much mass loss that you end up with only the core that is carbon or helium. I need to go
yeah.
reading.
Okay.
Rabbit hole.
Okay.
There is a rabbit hole.
Yeah. John Little asks, are globular clusters the remnants of galaxies that have been eaten?
No. Um, so it is thought that the way that you get globular clusters is two collapsing clouds of material or two infalling clouds of material can create a shocked thing of stuff between them.
Whoa, whoa, whoa,
And that,
whoa. A shocked thing of stuff?
yeah, I know words
Okay.
are hard.
Yeah.
So let me, if you have, for instance, two merging galaxies that have a lot of gas and dust, some of that gas and dust will get stripped out of them, end up in the spaces between them. And if that stripped out material or material that just happened to be there for whatever reason, gets shocked through the merger, that shocked material may be able to form a globular cluster. There's hints that this is what's happening in some places that we think we see young globular clusters. Exactly how you get a globular cluster instead of a dwarf galaxy is still a
Right.
point of contention,
And maybe
but it's looking
even-
like the shocking may be the cause.
Right. And it could be that a globular cluster, oh, what have you done to me? You've broken me. A globular cluster, the distinction between that and a dwarf galaxy is hard to find. That at a certain
So
point.
this was actually like my master's research. So there are little tiny itty bitty dwarf galaxies out there. The Ursa Minor dwarf spheroidal is the one I studied, that are single epoch of star formations. It
Yeah.
formed the exact same way as a globular cluster, but dynamically they're completely different, and they appear to have a completely different baryonic to dark matter ratio. And so the question becomes, how do you take two different blobs of mass and form them into things that are dynamically completely separate but have the same star formation history?
Right. Well, you know what? We've reached in for our hour.
Okay.
So it's time to wrap things up. What interesting things are coming up in your world?
So I am currently attending a conference that has me all kinds of excited, thinking about science communications and social justice and where the two of them meet. So I'm probably going to be driven to write an essay at some point.
I look forward to it.
So, beyond that, we're just continuing to keep improving our production around here, and we're still not quite up to the level of your guide to space with our daily space, but it's fun watching what Allie's capable of, and I'm hoping as we get things more under control to get back to software development and relaunching our citizen science.
Fantastic. Like I said, I've got an interview on Thursday about the mission. I'm going to probably be doing an update next week about all things SpaceX. I'm going to be interviewing an expert on what SpaceX has been up to. And then I've got Avi Loeb in February. He's the man of the hour right now, which, we'll
Are you
talk
going to
about
talk about his Oumuamua book?
that's the plan. We're going to talk about his Oumuamua book. But, it's possible that I'll be a little harder on him than last time. So, should be fun.
I can't wait to see that.
Yeah, yeah, yeah. And Nancy is posting the upcoming guests. We've got David Kipping, Avi Loeb on. That's gonna be weird. I'm gonna be interviewing him, and then like 3 days later, interviewing him again. So, and then we've got Jenny Radebach, Joseph Malozzi.
Oh, he's Stargate and there's this really cool sci-fi show that came out that involved Snoop Dogg and he was part of.
Oh, cool. Okay.
Yeah, he's done a bunch of awesome stuff, Stargate being, of course, close to my heart.
Yeah, the second best science fiction television show ever made.
Okay, I need to know what your first is.
Expanse.
Okay.
Yeah.
Okay.
Yeah. I decided a week ago that The Expanse is the best science fiction television show ever made.
See, Babylon 5, because it completed its arc, I feel comfortable saying it went places and innovated ideas that make it like right up there. But The Expanse is competing, so I don't know.
Yeah. I still think Expanse is better than Babylon 5. But Babylon 5 isn't streaming anywhere. We've been trying to watch it, just to sort of rewatch it. Carla's watching Farscape.
Oh, yeah.
Yeah, and I'm like, because I watched it way back in the day, and it was fun. I liked it. And I was like, so does it hold up? She's like, it's okay.
It's okay. It doesn't hold up.
Yeah.
I found Babylon 5 to stream a couple of years ago on a streaming service that was trying to compete with Netflix and must not have survived.
Yeah. All right, we should wrap up. Anyway.
It's worth purchasing.
Yeah. I watched all the Babylon 5s live way back in the day on television.
I got TBS, like I got cable for the first time.
Yeah.
So I could watch this season.
But that's fine. You know what? If people don't watch it, then people won't ask me about the name of my website anymore. Since it's the name of the newspaper in the TV show. No relation. All right. We're over with our hour. Thank you, everybody, for watching us today. Thank you, Pamela, for bringing the brain. Thanks to all our moderators. Thanks, everybody, over on YouTube and on Twitch. We really appreciate you joining us. Thanks to all our patrons. And we will see all of you
Friday.
On Friday. Yeah. Okay. Thanks, everyone.
Bye-bye. You can come up now. Come